So welcome to this pre-recording of lecture 38 of a course on symbolic computation. So the topic for today is kind of odd, but then I will justify why it fits in this course. So we are going towards the end of the course. And we have been using SageMath all the time. SageMath, which is based on Python. So in the previous lecture, I was explaining how SciPy can be used outside SageMath and what you need to do to use it within SageMath. So SageMath is essentially so much more than just a symbolic computing package. One can also do numerical computing. So this lecture fits very well within the scientific software aspect of this course. So, numeric computing with Python can be done with two very fundamental packages, Numpy and SciPy. Numpy is in essence the data structures package. In scientific computing, vectors and matrices are very important. Python does actually support an array type, but that's rather limited. One is much better off with NumPy, especially for multidimensional matrices. Then there is SciPy, which provides fundamental algorithms for doing scientific computing in Python. The URL at the bottom of the slide provides much more background about this project. Now, SageMath has NumPy and SciPy built in, as we have used this already to vectorize code. So this picture might be dated, but it is kind of a very good picture to demonstrate the computational ecosystem. So for a more updated view, visit the URL of the previous slide. So in this course, we have been using the Jupyter notebook with the SageMath kernel. We touched on Cython, and of course we are using Python, but then through a pre-parser. So in the last lecture, I briefly mentioned SciPy, and today we're going to look into NumPy and SciPy. So you can see that in this course we are kind of familiar with the innermost foundational layers of the computational ecosystem of Python. And also I should not forget to mention Matplotlib for all the plotting. Okay, so within this course we have introduced SageMath. It's also important that one can also use these packages outside SageMath. So that's also important to know. NumPy provides the data structures, and with it also the vectorized functions. So instead of applying a function on every element of an array or even on a list in pure Python, one can define that same function that takes on input an entire vector and then returns a vector on output. The main benefit of that is that the entire indexing of the elements is optimized for the memory layout. Also, the functions themselves are compiled, and that can speed up the Python code significantly. So this is so important that we have covered this in the first part of this course. So in scientific computing and linear algebra, speed matters. The backslash operator is available also in SageMath, also with Numpy. And again, this is the notational convenience, but using this operator means that one calls the optimized code in the software libraries. As I will illustrate in the Jupyter notebook that follows the slide presentation, one has to be aware that arrays are data structures, and that if one wants to compute with the matrices represented by the arrays, one has to convert properly to the matrix types. So if one solves a linear system, the typical calculation is to compute a residual vector to check the accuracy of the computation. For that, you can't really use the arrays. So I'll indicate how one has to be careful about this. So scientific computing rests on two pillars, if you like, linear algebra and differential equations. So here comes the pendulum again. We spent one lecture on differential equations, known as Calculus 4, but one can spend certainly not only one entire calculus course on this, but also a course on numerical methods to solve differential equations. And in a way, this presentation is kind of an advertisement for a numerical analysis course, which follows this course. So we have studied the pendulum. Here is a simple model, which already includes friction. And the plot is what they call a phase portrait. So we start here at pi over 10. So the horizontal axis gives the displacement, gives the angle. So we start in this problem with velocity 0. The vertical axis is the velocity. So we start at the point pi over 10, which is about 3.1, 0. And then we go in the opposite direction of the x-axis. So that means that the velocity vector is negative. There is friction, so as we come back at the other end, we are not at minus 0.3, but we are closer to the origin. Once we do one entire cycle, we are at 0.1 or a bit over 0.1, and the velocity is also decreasing. So you see it spirals in, so spirals, one would see them as spiraling out, but one should read this spiral as a decreasing displacement. So the angle, because of the friction, the pendulum comes to rest at 0 when the angle is 0 and when the velocity is 0. So in this course, the algorithms are not yet important. This comes in a sequel course. What is important, however, is that we can formulate the problem, and also that we can interpret the results that are given to us by the software. Okay, so let me now swap in the Jupyter notebook, which is still running with SageMath kernel. So one can run much of it also on Python kernel, which I will not do now. So what I will do is I will scroll slowly through the code cells, and indicate the most important aspects. So we started SageMath by saying that SageMath is a collection of various packages. So if we do a plot, so here we plot a point, then you see that the system that got involved was Numpy. So Numpy, I advertised this as a package to do computations and with data structures, with vectorization, but it also provides plotting facility. We can visualize a matrix, here a matrix of 400 random numbers, so 220 rows, 20 columns, with numbers between 0 and 1, and here plotted with a legend. One can see the extremal colors, but then for the outliers, so this is a normal distribution. I'm sorry, it's the numbers are not between 0 and 1. So the numbers are on average 0, and the standard deviation is 1, which means that 67% of all the numbers lie between -1 and 1. So this can be shown. So in some sense, this is showing that the dominant colors are the colors here in this color bar, green or blue, and with some orange or bright or dark orange or dark red. Okay, so we import NumPy as NP, and when we then really want to have a random matrix that is generated with NumPy, we apply the np.random and we ask for a normal distribution. So on this matrix, the plot works fine. Now let's use this to solve this linear system. So we have generated 400 random numbers, a 20 by 20 matrix. And there is a bug in the, so they are not uniformly, but they are normally, or I'm sorry, so above they were uniformly. But I see that the random numbers of the right-hand side are uniformly distributed in the interval. So that is important. It's important that I actually don't improvise. So the A is normally distributed, the right hand side is uniformly distributed. So here you see the solution vector of a random solver. I mentioned the backslash. One can also apply the solve method from the linear algebra module. Now these 20 random numbers don't really say that much, except that if you solve a linear system with small numbers, relatively small numbers, that then also the solution also consists of small numbers. Okay, if we want to compute, if you want to verify the accuracy, then we compute the residual vector. So this is b minus a times x, and we compute the norm. So the linear algebra package of NumPy exports the norm, and you see that this norm is far from being 0. So something went really wrong, and what goes wrong is that the type of the B, the A, and the X, they're all NumPy arrays. So that they are just containers to hold data. So the operator arithmetic kind of went through, but it was actually completely wrong. And that is something one needs to be aware of. So even though there is no mistake, there is a mistake, and the worst mistakes in using software are the mistakes that actually go unreported. So one could now think that the vector x, this numbers here are all wrong and one should not trust solve. That's of course not true. What we should do is that we must convert the array types into matrix types, and that is happening here in the execution block 6. We are transferring, casting the array data type into the NumPy matrix data type. And for that, then you see that the same instructions, but now on different variables, the variables of matrix type, that they work out fine. So the machine precision with 52 bits fraction is about 10 to the power minus 16. So we have a result which is close to the machine precision. So that's the linear algebra part. Be aware that within NumPy, one can work with matrices. One has the operator arithmetic. We can multiply, provided that the dimensions work out. We can subtract, so we can do the matrix vector calculus, but only on the types of matrices, not on the data structure type, the NumPy arrays. Okay. I will go to differentiation, to differential equations, but in between we have the integration. So another important topic in scientific computing, because for many functions there is no explicit antiderivative. So the symbolic antiderivative on the example here will not work. Well, in some sense it does work, but then what happens is that you see the integral representation. So perhaps the proper way to work would be to say we will hold true, and I will just show the output. So I knew for this example that there wouldn't be any symbolic antiderivative. Also, one may not desire one. So let me then run this, and you see that then I get a numerical value. Now, numerical integrations are a lot harder than solving equations. So it's a lot harder to verify the correctness here. But let me take again a side step. So what about who did this? So, well, it turns out that this calculation, so I have to execute this, this calculation was done by Jinak, if I pronounced that correct. So the G is more like also the GNU Linux. It's actually not a computer algebra system. So the software library is a library it's a C++ library for scientific and for symbolic computation without a computer algebra interface, or without an interface such as one would expect that would be for a normal computer algebra system. So of course there are Python bindings, and that is what makes it still a very useful software system. So in the output 2 here, I mentioned how do we verify this? Well, we can call a numerical integrator, which provides us with more diagnostics. And I will do this now here with quad from quadpack. And I have the function defined. The function is defined here. It is this f, the exponential of the sign. So the wrapper takes in Python functions, or actually NumPy functions, which are properly vectorized. we have the bounds, and then we ask for the full output. So this will tell us, it will, of course, so it's kind of impressive at first, perhaps a little bit too much information. The first number is the value. The second number is the estimate for the accuracy. And you see, this is a very efficient integrator, or you could say it's a very easy integral to integrate numerically. Only 21 function evaluations were needed. So, and actually one can get the function evaluations as well, I suppose. So here one sees the extra values from the data, but the most important information comes from comes from the error estimate. Okay, we are halfway, and I have still two topics to consider. So approximating functions is very important. We have seen this, how to compute Padé approximants within SageMath. So one can see this as a symbolic computation, that we are approximating functions like the sine functions and the cosine function. We are approximating this with rational forms. So the result is a symbolic expression, and one can see this as an entirely symbolic computation, but I hope to indicate now that we can see this as a symbolic numeric computation. As one wants to evaluate the approximation at floating point numbers, one may as well compute the approximation as well with floating point arithmetic. Okay, so let me run through the cells. I will use SciPy for this. And in the last lecture, we pointed out that one of the features of SciPy is that one could compute the terms of a Taylor series expansion one after the other. So the sine function is an odd function in the sense that it's odd for other reasons, but it's odd in the sense that only odd powers appear in the Taylor series. So we will use the first 6 ones. But actually it will turn out that when we look at the coefficients, that we will have 3 zeros sitting in. So we could have been a little bit more frugal in our computation, and we actually only needed the first 3 ones. You see the difference now in the generator. The generator skips the terms with 0 coefficient. If we look at the input for the Padé approximant, we need the coefficient vector as a coefficient vector given as a NumPy array. So this is a combined, an explicit combined computation, and in some sense you may appreciate the convenience of Sage more, that a lot of the type conversions when one uses Sage, they happen automatically. Here we must do the type conversions explicitly. I will repeat what I explained in the last lecture. In order to use the feature of the generator in a series of SciPy, one must use the symbols of SciPy. So here this is done alternatively. We use the var construction, but there is the alternative construction. You can import the symbol x from the SciPy ABC. Otherwise it does not work. So here you see that we have to sum up the terms, and the summing of the terms actually gives us an expression, and most likely this expression is actually of type, and let me now guess, it's either of type SciPy, or I will guess it's SciPy if I'm consistent with my explanations from before. Okay, so I have to execute this. It is indeed a SciPy. It's a SciPy expression, but on the SciPy expression I can select the coefficients. So this is an intermediate, because you see that if I'm going to execute this now step by step, so I'm going to use Numpy, but intermediately. So in order to improve this notebook a little bit, I should have indicated more how this works step by step. So I'm not yet using Numpy in this block. So I'm using Numpy in the conversion. So with the C, I'm still in the Python world. So C is of type list. So C is a Python list. In order to compute a Padé approximation with the SciPy tools, I must convert to a NumPy array. So a NumPy array can convert any. So and this is an array. So I'm sorry, the C is of type list, but the objects that are in there are, as you can see, rational numbers. So with the conversion to the array type, I'm also fixing the type of the data elements. And perhaps I should have pointed this out earlier, but now is really a good moment. The main distinction between an array and a list is that all elements are of the same fixed type. So I'm using the float type, which is the double precision floating point default number, and every number is occupying the same space. Okay, so now we are ready to go to SciPy. So we have used SciPy, NumPy, and now we are ready to use SciPy. So I'm computing, I'm actually solving a linear system, a very structured linear system. If you know, and this will come in a numerical analysis course, if you know how Padé approximations are defined, then you can take it from the coefficients. But the Padé wraps this rather nicely. So we have to know where it is. So it's in the interpolate package from SciPy, and I'm asking, so we need to provide an argument. I'm asking for the degree of the denominator to be 2. I can also specify the degree of the numerator, but once the denominator is fixed, so at least I have to provide the denominator, then the numerator will be defined. So, and we can verify this. So we have a polynomial of degree 2 as the numerator. The constant term is fixed at 1. So one does not want to divide by 0, although there are still very bad values for x for which division by 0 will occur. But there are 2 coefficients needed for the denominator. And for the numerator, which is now 4, because it's a cubic, we will have 6 coefficients in total. And this 6 lines up with the input coefficients. So you may have wondered why I was using 6. Well, 6 was rather arbitrary. You need to return back to the initial computations if you want approximates of higher degree. So the 6 is what is tight. It is what is strictly necessary to give you such a Padilla approximant. And here you see how this Padilla approximant really approximates the sine function really well. So the Padilla approximant agrees with the Taylor series. So the Taylor series are locally very good. But you see, and locally that means that with the series, you should not go much beyond -1 and 1. With a Padilla approximant, one can extend this. So you can see that on the picture, it goes very well to past pi over 2. So it's only at the very end that you see that there is a gap between the approximation drawn in red and the sine function. So that means that for many practical purposes, we can replace the sine function by a quotient of two polynomials. So for the plotting, I specified that the plotting was, the beginning was actually done by Numpy. Here actually I do not need to convert. So the expressions that I'm getting are the poly 1Ds, which are defined by, which are one-dimensional polynomials defined by their coefficient vectors. They can be very easily evaluated for plotting. So these poly 1Ds can be treated as functions. Now, if you want, and here now we come back to SageMath, if you want to see the polynomials really as nice polynomials, not as coefficient vectors, then one can cast them into the symbolic ring. And that is done here. So by casting into the symbolic ring, then you can compute with the expressions. Now, the casting can happen in both ways, in two ways. So here, this is illustrated with these two statements. Either I can evaluate, so we are running Numpy within a Python environment that is pre-parsed. So we can evaluate at symbols. So these are kind of hybrid structures. So here in the input cell 25, I'm evaluating at the SciPy symbol X. And what I get is actually a SciPy expression. Alternatively, if I convert the expression to a symbolic ring, then I do have a SageMath expression. So alternatively, the third way, which is not shown here, is that if you would declare a symbol that is a SageMath symbol and then evaluating that FP0, that would also have been given you a SageMath expression. Okay, so this section shows the interplay of SciPy, Numpy, SciPy, and SageMath, done with explicit data type conversions. So it are actually the data types that are defining how the computations are running. Okay, one last section on solving differential equations, which is very important in scientific computing. So let's take the one module of the pendulum with friction. So at the very end, I will get to the phase portrait that I try to explain on the slides. So we have the numerical setup. So in lecture 31, we showed how to solve this problem, how to deal with this problem numerically, but then throughout the symbolic setup. Here we go immediately to the numerical setup by defining the right-hand side vector. So we have a second order differential equation. We're going to rewrite this as a system of two first order differential equations, where the two unknown functions are the displacement, here the angle theta, and the velocity. So the right hand side, the first type of the right hand side, expresses that the derivative in theta is the velocity, and then the second right hand side, the second component of the right hand side here, expresses that the derivative of the velocity is the second order derivative of theta, and this is here the original right hand side. The friction term, and then the term that comes from the gravitational force. We have to define, so let me execute everything. So we have to define a Python function, and the Python function runs in SageMath, which means that I can actually evaluate this symbolically, and you see that I get the same thing back as the right hand side of the ODE. So now let me continue this. Then comes the solving. And here the solving should have been splitted out into several parts. So at least I should have broken off what is returned. There is the setup. So we have to determine how many points we want. This is important in the granularity in the resolution of the plot. So we'll be using 10 points. I will let this pendulum go into this time span going from 0 to 10. And so the time span is using this linear space from Numpy. And I will be using the ODE int, which comes from ODE pack. So SciPy is one of the foundational packages in scientific Python. But the reason why it is so foundational is that it collects many standard packages, many packages for which there is a consensus in the community that, at least at some point, that these are the best software systems. So ODE int is a classic software package for solving ordinary differential equations. It's a numerical software package, so what it returns are numbers, and in particular we are in the NumPy world. It returns an array of two columns, and you could say, well, hey, with these numbers, what do I get there? Well, remember that pi over 10 is the initial condition, and that's now good that I point this out so that I stop here a little bit. So what we give as the argument of the solver is the right hand side and the initial conditions. So we have the initial displacement of pi over 10, which is 0.31415. So you see the pi over 10 sitting in here. And we have the zero velocity. So the two columns in the solution are the computed values for the angle and then for its velocity for the time span. So what is not plotted here, what is not shown in the output, is the time span, and we have to be mindful of that when we plot the points. So if we want to plot the points, so here I'm using a list plot, I'm first defining the tuples with the coordinates. So in this plot, the horizontal axis is the time axis in going between 0 and 10, and then the vertical axis is the contains the values for the angles. So again, at time equals 0, we start at pi over 10 and we observe the damping. So at time equals 10, the pendulum is actually at position 0. So there is no displacement angle anymore. So one could have argued at first that why do you have to introduce another variable, the velocity? But the velocity makes for an interesting final plot, and that is this inward turning spiral. So what we see here are the coordinates now, and this would also make a very nice animation, which would be very good for showing the direction of this plot. One might be inclined to think of spirals as moving outward. This is an inward moving spiral starting at the point pi over 10, 0, and moving inward into the origin where the pendulum is at rest. Again, list plot is used here. This is a nice combination of Python, so the list comprehensions in Python. So we have the time range of the 1000 points, but the time is actually now factored out. What we see in this, so this is a purely geometric plot, how the velocity relates to the displacement in this model. Okay, I hope that this lecture was interesting, and I will conclude this recording.